So yeah, there's an error show today, by the way, so that could...
Wait, really? Welcome back to Coding with Qiskit. I'm your host, Jin. If you're joining us for the first time, in this series we talk about quantum algorithms each week, so be sure to like and subscribe. A few weeks ago, we talked about how a quantum computer can find a certain element of a database faster than a classical computer using an algorithm called Grover's algorithm. This week, we're going to talk about how to extend Grover's algorithm in order to do an optimization problem called the satisfiability problem. So let's talk about what the satisfiability problem is. Let's imagine that I want to order something for lunch. So obviously, I want to order from someplace that's open. They're nearby, they deliver, and maybe I'm feeling Thai food. So I've just listed my 4 constraints there. My question is, if I have a list of available restaurants, which restaurant satisfies all 4 of my constraints? By encoding my constraints into a quantum oracle, I could theoretically figure out which restaurant I should order from faster than if I were using a classical computer. For a reasonable number of restaurants, my phone can do this just fine. But what if we're thinking about big data sets? For big data sets, we can have a quantum speedup because we can recast this problem into a search problem. We can search over every combination of inputs and determine which input evaluates to true given our constraints. Another useful example of a satisfiability problem that we're going to implement today using Grover Search is the Grover's dinner party. So imagine I want to invite some friends over for a party. I'm going to invite Abe and Olivia, and they're good friends from Qiskit Camp, and I also want to invite my friend Amira. However, Abe and Amira just had a big fight and they don't want to hang. So how can I invite as many friends as possible while making sure everyone gets along? Fortunately, Grover Search can be used for Boolean satisfiability problems, and the constraints for our party planning problem can be formulated with the following Boolean expression. So we can have Olivia and Abe, or Jin and Amira, and not Abe and Amira. And we can simplify this a little bit just by saying A and B, or C and D, and not A and D. So let's see what this looks like in Qiskit. So I'm going to first activate my environment, going with Qiskit. This is where I have Qiskit installed, and I'm going to open up a Jupyter notebook. So from Qiskit, I'm going to import my simulator, basic air. From Qiskit Aqua algorithms, import my Grover search. From Qiskit.aqua components.oracles, import my oracle. From Qiskit tools, visualization, import plot histogram so I can see my results. So I'm going to encode my logical expression in here. So it's going to be Olivia and Abe, or Jin and Amira. Okay. And not Abe and Amira. Okay. And I'll plug this into my algorithm, which is my Grover search, logical expression, oracle, plug in my logical expression. Okay, good. I'm gonna get my backend. So I'm gonna grab the basic air simulator, from which I'll grab the Chasm simulator. Okay, good. Now let's run this algorithm. Okay, good. All right, let's plot our results. The measurement results. Possible party combinations. Bar labels is true. Okay, good. So what we're seeing here is the possible combinations of people I can invite to the party. So each number represents whether or not each person should be invited or not, and these are organized alphabetically. So this will go Abe, Amira, Jin, Olivia. So one possible combination is Amira and Jin are invited. That's what this first column is saying. The next possibility is Abe and Olivia should be invited. The next possibility is Abe, Jin, and Olivia should be invited. And the last possibility is Amira, Jin, and Olivia should be invited. So why run this on a quantum computer? In this small example, my laptop can handle this calculation just fine. But suppose we want to add 6 more people to the equation, and each one of them has their own constraints. If I had a total of 10 guests, the number of combinations blows up to 1024, and every time I add another guest to the list, this number doubles. So solving this problem on a classical computer would take of order n time, where n is the number of combinations, versus of order square root n time on a quantum computer. Why don't you try to map Grover's algorithm onto your own satisfiability problem? And let us know what you get in the comments below. That's it for this episode. Make sure to like and subscribe. And tune in next week where we'll talk about quantum machine learning. See you then. This week was brought to you by Dunkin' Donuts.
Dunkin', it's just Dunkin' now, isn't it?
This week was brought to you by Dunkin'. Quantum runs on Dunkin'.